Thank you very much, Birgit. And so I would like to thank the organizers, so Birgit, Roland, and David. It's really a pleasure to be here at the Schrödinger Institute. And so I forgot to say my talk is based on joint work with Yvan Martel. Okay, so here I'm interested in the generalized KdV equation. So this equation, dtu plus dxu5 plus dx2u is 0. And u is a real valued function. And here I look at for solution defined on the line. X, so it's a space variable, and t is a time variable. Okay, so this equation is invariant by, so it has two groups of invariants. So the scaling, which is with this lambda 0, for any lambda 0 positive, you can rescale the equation on this form. And also the translation, so you can do a spatial translation, and this leaves, you still get a solution of the equation. Okay, and so if you look at the L2 space of square integrable function, then you can see that the L2 norm is preserved through this transformation. And so this is due exactly, that's because we took here the power 5, so we get an L2 critical equation. Okay, so this will be very important in this talk. So the equation, the one we're looking at, this is L2 critical. Okay. And moreover, so, well, this equation for this power is not completely integrable, but we got 3 conserved quantities. So the integral of u should be conserved along the flow. The L2 norm of u should be conserved along the flow. And you also have an energy, which is conserved along the flow and which is defined in H1. Okay, you have the L2 norm of the gradient. So the energy space, the natural space to study this equation is H1, the classical H1 space. Okay, so what you want is a local theory if you want to study, and this was done in the 90s by Koenig, Pons, and Vega. Okay, so more precisely, they prove that the problem is locally well posed in H1, and so this means that for any initial data in H1, there exists a positive time, and this time only depends on the H1 norm of the initial data. And there exists a unique solution of gKdV starting at time 0 in U0 and describing a continuous curve in H1. Okay, so unique in the sense that to construct the solution, you have to be in a smaller function space. So you have to add some norm to run the fixed point argument. And so it's unique in this smaller function space. And moreover, of course, the flow map is smooth. A corollary of these results is that, so, well, if you fix an initial data, then you know that you have a local solution and you can look at the maximal time of existence. And a direct corollary is that if the maximal time of existence is finite, then the L2 norm of the gradient of u blows up in L2 with a blow-up rate which is larger or equal to 1 over t star minus t to the power 1 third. And this is the self-similar blow-up rate. So the proof is very simple if you know the well-posedness theory. So let me just go over it. You fix, so assume that t star is finite and then fix a t0 strictly smaller than t star. Okay, so then you look at this solution, okay, which due to the scaling invariance is also a solution of gKdV. And this lambda 0 that you will rescale, it will be, you will see why we will take it exactly equal to the L2 norm of the gradient at this time t0. Okay, so if you look at the L2 norm of V in 0, okay, so it corresponds thanks to the L2, the invariance of the scaling by the L2 norm to the L2 norm of U at time t0, and this is conserved around the flow. So this is the L2 norm of U in 0. Now, if you look at the L2 norm of the gradient of V in 0, by the same arguments, you will find that this is lambda 0 minus 1 the L2 norm of the gradient of u in T0, okay? Because you have just differentiate one in space, so you have this lambda 0 minus 1, which come up here. And so that's why we chose this lambda 0 here. Okay? So you can make it equal to 1. So at the end of the day, the H1 norm of V in 0, it's independent of T0. Okay? So if you reapply your local theory, then you know that there exists a positive time independent of T0, such that your solution V is defined at least on this positive time. Okay? And then if you look at your solution, what is V actually is this guy here. You know that T star has to be larger than T0 plus this S over lambda 0 cube. But if you rewrite this, it gives you exactly our lower bound for the blow-up rate of the solution. Okay, so this is a very classical argument. It's just based on the scaling invariance, the local theory, and the conservation of the L2 norm. Okay. Here it's just a very heuristic computation where I try to convince myself why 1/3 should be the self-similar blow-up rate, just by taking a profile which I rescale, and I rescale at a power t to the power nu. So saying that it is self-similar, it means that every rescaling of this solution should be the solution. So if you apply this to phi, well, then a direct computation will tell you exactly that actually, since this has to be true for any lambda naught, you have nu has to be 1/3. Okay? So this is somehow to convince myself that this is the self-similar blow-up rate. And so what we saw that from the local theory, if you have finite time blow-up, then the blow-up rate has to be larger than or equal to this 1/3. Okay, but now coming back to the classical fact of this equation, so the dynamic, you have very important special solution, which are the solitary waves. So there are solutions moving to the right, and here I'll call Q the one with speed 1. Okay, and so I want them to be localized, so going to 0 at infinity. Okay, so if you plug this into the equation, you see that Q has to be a solution of this nonlinear ODE. And well, this is a calculus exercise. You can solve it, and you can see that it is an hyperbolic sequence to the 1/2 in this case. And since we are L2 critical, this is very important. So then the energy of Q has to be 0. It's just a Podzaev identity with this equation. So of course, once I got one solitary wave, I can use my family of transformations, so I can rescale them and translate them. And so I got a 2-parameter family of special solution of the equation, but they all got the same L2 norm because we are in the critical case. Okay. Okay, so now a word on the global solution. So this is very classical. So now we want to look at the Gagliardo-Nirenberg inequality and the one which controls the potential term in the energy, so U6. And you can see that the base constant is given as a function of Q, solitary wave. Okay, so if you use this argument, then you look at the energy of U, it's conserved over the time, and then you got a lower bound by this guy, and here I also use the conservation of the L2 norm. And so finally you see that if this is strictly positive, then you got a control on the H1 norm. Okay, so on the L2 norm of the gradient, but the L2 norm is conserved. So if you take U0 in H1, with L2 norm strictly smaller than the one of Q, then first the energy of U0 is positive, and second, you get a control on the H1 norm, and so you can reapply the local theory, and you got arbitrarily large number of time, and so you got global solutions. Okay, so this is very classical. This is from the 90s. And as I was saying, the L2 norm of any solitary wave is the same. So like a very natural question is to know what happens when the L2 norm is larger or equal to Q. Okay, so here, so since we have the Schrödinger Institute, I also have to talk, even if this morning we had a lot of talk on Schrödinger, but this will be very, very basic. Just a digression on the L2 critical focusing nonlinear Schrödinger equation in 1D. Okay, it has, so this is this equation. The only difference here is that U is a complex value function, so you have a system. But somehow it has the same features as the L2 critical gKdV. So you also have standing waves. You have the same energies. The L2 norm is also conserved, so you can do more or less the same analysis. But in this case, you have one more ingredient, which is a virial identity, which is that the second order derivative of the momentum is equal to twice the energy. So the energy is the same here. And so this is also conserved along the flow. So if you take an initial data, which is in H1 and also for which the momentum is well defined, and you choose it such that the energy is strictly negative, then you got a second order parabola, which goes to minus infinity and plus infinity. So you know that at some time, let's call it T dagger, this has to be zero, the momentum. And if you use Heisenberg inequality, so the L2 norm is conserved, and then Heisenberg inequality tells you that it's bounded by above by the momentum times the L2 norm of the gradient, then you find that since this is strictly positive, this guy is going to zero. This guy has to blow up in finite time for a time not larger than T dagger. Okay, so this is in the 70s. This is classical obstruction arguments. But of course, this argument does not tell you anything neither about the blow-up rate or the blow-up profile. Okay? But it's somehow a very useful tool. And I will come back to this, but then, well, there have been some work of Bourgain-Wang, Perelman, and then of Merle and Raphael. And of course, there was numerical work before, but they prove in the 2000s, so the log-log blow-up for the L2 critical analysis. Okay, so a stable blow-up with a log-log correction very close to the self-similar blow-up rate. Of course, such identities, at least on this form, are not available for gKdV. So for gKdV, you have to somehow go in this direction and do a more refined analysis. Okay, you cannot have a direct answer to the question of the blow-up. Okay, so, well, there have been a lot of work since the 2000s. So in the case of slightly supercritical mass, so you take an initial data with a L2 norm a little bit above the ground state. So there were numerical evidences of blow-up, but the first results, rigorous results, if you take negative energy, is due to Frank Merle, so in 2001, and then he proved that this solution blow up either in finite or infinite time. And the proof relies on the virial estimate by Martel-Merle, but not similar to the one we saw here, a more tricky one, which rely on non-standard spectral assumptions. Then Martel-Merle also works like to improve these results. So they were able in a paper here to rule out the self-similar blow-up rate. So it means that if you have finite time blow-up, the blow-up has to be with a rate quicker than this one. And also they prove that like the profile has to be the solitary waves, okay, which is somehow natural for L2 critical equations. Moreover, they have this identity on the geometric parameter, so the dilation parameter and the translation parameter. Finally, they also, not finally, but around the same time, they also prove, so it was the first rigorous proof of finite time blow-up for a solution close in L2 to the ground state, to Q, with negative energy, but they had to have, another hypothesis, which is a decay on the right for the initial data. And as you will see, this turned out to be important. So these results were revisited 10 years later, so in a joint series of work of Martel, Merle, and Raphael. And so this time they are able to give a complete classification if you take an initial data in this space A. So it's a perturbation in H1 of the ground state, but you see you have to add an assumption on the decay on the right of this solution. So well, this is technical here, so this is probably not sharp, but you have to assume some decay on the right on the solution. And then you have three possibilities. So if you take such an initial data, either the maximal time of existence is finite, so you have blowup. So it means that for any time you will stay in the tube close to the soliton manifold. The soliton manifold is a manifold of all the family of solitary waves, which are translated and rescaled. Okay. And then the blowup rate will be 1 over T star minus T. Okay. So it's quite far from the self-similar. Then another possibility is the soliton. So it means that T star is plus infinity, and somehow you converge, close to the solitary wave. So a little bit on the left, and you take all this region to the right to a rescale solitary wave for lambda infinity close to 1. And the last possibility is the exit. It means that there exists a small T star, which is strictly smaller than a capital T star, for which you exit the tube. Okay. And then, as far as I know, it is still open to know what happened with this solution, even though it is conjecture that the solution should scatter. And moreover, there is another work of Martel, Merle, Nakanishi, and Raphael, where they prove that this case here, actually, it's a codimension 1 manifold separating the blow-up and the exit regions. Okay. Little bit more on this. They also prove the existence of a unique minimal mass solution. So it's a blow-up solution with mass exactly the one of the ground state. No, it's not slightly above, it's exactly equal. And it's the same blow-up rate, 1 over T. But, well, the interesting part that if you look at this theorem, you could wonder if this assumption was purely technical or not, but actually it's not the case. So somehow, if you take initial data outside of this class, so without this strong decay on the right, then they were able to construct close to Q solutions which blows up with 1 over T star minus T to the power nu, and for a continuum class of nu. So nu, in this case, larger than 11 over 13. And this is probably not sharp, as we will see, but they also could construct solution blowing up at infinity at any rate, any polynomial rate. I think even exponential rate. Yeah, so as I was saying, the lower bound is not sharp, and we think it could be extended to 1/2. We think this is just purely technical. Yeah, so, but there is something interesting regarding this 1/2. You remember this identity here? So when you took nu 1/2, this is exactly the threshold which will give you that the blow-up point is going to infinity. Okay, so somehow the bubble is focusing the solitary wave, but it's going very fast to infinity at the blow-up rate. Okay. Yeah, another result in the same vein, joint work with Yvon Martel, we also prove the existence of a class of flattening solitary waves. So it's wave, in this case, they are decreasing, but this is not scattering. Okay, we can really clean around the wave. So it's another interesting phenomenon. And here, I should say that this result of a continuum of blow-up rate are not the first one for nonlinear dispersive equation. And there is this result of Krieger, Schlag, and Tartaro in 2008, 2009 for wave map and energy critical wave equation. And then I know that there are a lot of experts in the room, and the wave equation is not my world, so please forgive me if I don't cite all the results here. But somehow, I would say that these one are the first one in the L2 critical case. Yeah, and so now I can finally state our results. So we are able to construct solutions which blows up at another rate, so 1 over t minus t to the power 2 over 5. And some of the new things here that the blow-up point is going to 0. Okay, so this time the blow-up point is not going to infinity, but so the bubble is focusing, but at a finite point. Okay, and well, we can take this solution as close as we want as Q in L2. And somehow this was surprising for us because we did, when we tried to work on this problem, we wanted to prove that it was not possible. So we didn't expect this, but at some point we couldn't prove it, and we start thinking the other way around, and then we're able to construct this counterexample. Okay, so we'll have a little bit of time. Okay, so if I want to summarize the results for gKdV, well, as we saw, by using the local theory, you can rule out blow-up rate smaller than the self-similar. The self-similar was ruled out in this paper by Martel-Merle. And then this is the stable blow-up. Okay? And then you have a continuum. So this could probably be extended up to 1/2. But you see here, we really had no idea whether you could have something or not. And now we have this specific example here. I should also say a word on if I change a little bit the equation, so I increase a little bit the power in the nonlinearity, then there are examples of self-similar blow-up, so numerical example, and also rigorous construction. So based on the self-similar profile constructed by Herbert Koch, and so Lan proved rigorous self-similar blow-up when you're slightly supercritical. So if you want, we can have a comparison with the critical 1D critical NLS. So in this case, self-similar is 1/2, and then there is a log-log correction. So this is the result of Mel-Raphael, and this is open in H1. Then, yeah, so this is the one I was talking about. The 1 over T, so there is a conformal blow-up, and there is also a solution construction of Bourgain-Wang. This, so Pierre-Raphael ruled out solution blowing up at the rate so between the log-log and the power 1 over T when you're close to one bubble. Okay. So somehow here there is nothing. So you can see that it seems that it is quite different feature between gKdV and NLS, even though when you look at them first, you would think that they are quite similar. And here, as far as I know, it's completely open if you have blow-up rate with larger speed. Okay, so yeah, sorry, yeah, this is a very good point. So, like, we will work a lot to have finite energy data. Yeah, so sure, in L2, then we don't know. So maybe more things are possible. This is a very good point. Okay, so the strategy of the proof. So the idea, so this, like, we rescale the problem. So we take a rescaling. Lambda is a parameter, so the dilatation parameter, which is depending on t, and so we go to zeros. And sigma of t is a translation parameter. And so by using a chain rule, you can rewrite the equation on this form. Now, if you take the variable w, you can also rescale the time, okay, which is natural through the scaling. And if you do this, you will get this equation here. And this is the term that you get when you derive with respect to lambda. Okay, so this or small lambda, so this capital lambda, I like to call it the scaling operator. So it is 1/2 of w plus y dyw. And then you also get something when you derive with respect to the translation parameter. Okay, so here this -1 is the same here that we add on both sides so that we get the solitary wave equation here. Okay. So, well, if you look at a blow-up of the form lambda t, t nu, okay, so 1 over t nu, well, then a direct computation, like you can integrate, tells you that S is t minus 3 nu minus 1. So you see that if you're above the self-similar rate, when t is going to 0, S is going to infinity. Okay, so somehow this lambda has to be a power of S, and lambda S over lambda will go to 0 at infinity. Okay, so this will be small, and this will also be small. Okay, so I can rewrite the equation here. And somehow, if you look for a good ansatz, of course, you're in the L2 critical case. So the first order approximation that you want to take is the solitary wave, okay, because it doesn't depend on S, and this is the equation of the solitary wave. So somehow you have to start with this. But then it is not enough. So if you just have this ansatz, you will not be able to close the estimate. So you want to refine your ansatz. Okay, and this is the difficult part. And here, so we look for an ansatz Q plus some small v. And now, well, plug that into the equation and derive the equation for small v. Okay, so what you get is dsv plus dy of lv. L is the linearized operator around the ground state. And then I just keep here lambda of q and dyq. Okay, so everything else, I put it on the right-hand side, and so I will have a big O of nonlinear terms, so either v to the square or v times modulus of m, which are the equation for the parameters. Okay. Yeah, so somehow I want to find a good approximation of this solution. So what happened, what is the ansatz for the stable blow-up rate? So it's 1 over t. And the ansatz is this, this p, which is a solution. So to dy lp is lambda q. And here, well, this is typical of the gKdV. You have this dy here. So if you integrate this, and you see that the integral of lambda q is non-zero, you know that you cannot find a localized solution of this equation. So somehow your profile, it has to be non-zero either at plus or minus infinity. Okay, so here in this case, they took it non-zero at minus infinity, so they took a profile like this. Sorry, I think, actually, I think it does something like this. So this is the P. And why? Because, well, for KdV, somehow the solution is moving to the right and is sending dispersion to the left. Okay, so it's somehow natural to take something which is 0 on the right because you don't want anything to come to you. So this is the idea. And then, so the idea was to take an ansatz of the form with separate variable. So you would take P, and here you would take somehow it's a parameter, but it's at first order this guy here, so that you can cancel this guy here. So this is quite natural. And so what do we do here? We change the ansatz. So instead of working with this P, we work with a guy we call A, or A1, because there will be a series of them. And this A is odd. Okay, so if you want, you translate your P. It's not exactly translate, but you do something like this. Oh yeah, sorry. It's M0. So your P is, your A is something like this, and this is minus M0. And this guy somehow it can be deduced from P, and it is related to a resonance of the operator dyl. So a resonance, it's an eigenvector which is non-localized. And for us, it really plays an important role. Okay, so we can deduce E1 from P by using a resonance. And then, so I think this is the main idea somewhere of the paper. We do not take any more ansatz with separate variable in time and space. We somehow mix the variable, and this is the original variable x. Okay, so our solution is looking like this. Yeah, so maybe I will try to draw something on the other blackboard because it's important. I still have a little bit of time. Okay, so let's say that I'm on the y here. So I have the solitary wave, which is focused and very focused in y. So it's like this. And here, what we do, that so we have the function a1, which is like this. This is a1. But actually, what we do is that we multiply this a1 by a bump function, but which is localized in x. So it is centered at minus sigma over lambda, and minus sigma over lambda, in our case, is still large, but smaller than lambda, so it's somewhere here. So somehow what we add, and this is a bump function, okay, so what we add is something like this, but then it's multiplied by y. Okay, so it does something like this. So you see, so what we do is that we make the wave interact with something which is non-symmetric. And I think this is so one of the novelty, I think I would say the main novelty of the construction is this new kind of ansatz. Okay, so let me try to convince you why it is good. So yeah, so first, when you plug these ansatz here, if you think that you disregard the ds derivative and you think that dyl will fall directly on lambda q, you got an so you will get an equation like lambda s over lambda has to be equal to 2 lambda to the 1/2. Okay, and this you can solve it formally, and you find lambda s is s to the -2, and then you can come back in the original variable, and this is the blow-up rate we have. Okay, so this is really given here. Okay. And so let me try to convince you why it was important to do this. So somehow why we could see new blow-up rate with this construction. You have to look at the energy. And so this is connected to the question of Daniel. When you look at the energy, so this is rescale. So if you come back in the y variable, you have to divide by 1 over lambda square. And this lambda, it can be very small. And like in our case, is 1 over s square, but the closer you are from the self-similar value, the smaller it is. So you will divide by a very, very large, sorry, you divide by a very small parameter. So somehow 1 over lambda is very, very large. But the game here is that we want to construct finite energy solution. So somehow we have to deal with this. Okay. So if you develop Q plus V, the first order is the energy of Q, and this is 0 as we saw, and this is fundamental. This is why the profile is really, the bubble is really given by the solitary waves. But the next order, if you do the computation, is minus Q prime prime plus Q5, and this is equal to minus Q. So somehow the next order is QV, and that's why if you have an odd function here, this will give you 0. Okay, so somehow you gain something to have used an odd function. And this is why we are able to continue. Of course, for this computation to work rigorously, it's not enough to cancel this term. We have to add several, so this is I would say the technical difficult part of our paper, that we have to do several corrections, so I think 5 or 6, in order to get the finite energy here. Okay, but I think really it starts because you can do this. Here, you can cancel this guy. If it was not possible, we could not see this kind of blow-up rate. Okay. So finally, a comment which is connected to this. So you see, we want to make the wave interacted with this asymmetric profile. So if you come back to the original variable, you get something like this. And so when you do t goes to 0, what you got is a concentration. So the blow-up point also goes to 0 here. And what you will get is that this guy will become a sine function. So somehow what we call the blow-up residual, what remains when you take away the bubble, it's a sine function. So it's something which is in L2, but is not in H1. Okay? And so this is like it's a personal thought. So it's not a proof or something, but it seems to me that the blow-up rates closer to the self-similar rate, they may be related to low regularity of the blow-up residual. So somehow in the classification, the 1/t, then the residual is H1. But for example, when you look at the log-log blow-up, the papers of Mel Raphael, then the blow-up residual is only in L2. So this may be something related here. Okay. I think I'm almost done, but just a last slide. The rest of the proof is more classical, but just to comment a little bit. So it relies on the compactness arguments introduced by Frank Merle in the 90s in the NLS setting, and it was also revisited by Raphael Scheftel for the non-homogeneous NLS. And it goes as follows. So take a sequence of time. So for us, S to minus infinity, it corresponds to T0. Okay, so it is your blow-up time. So sequence of time going to the blow-up time. And then you consider the sequence of solution which starts at this sequence of time, which are very large, close like exactly as our approximate solution. Okay, so you can think that it is a very focused profile. So the idea is then to study the solution, Wn. So you split it as your approximate solution plus a rest. And all the game, so it's to get nice estimates on the rest, epsilon n. And you want to have this bootstrap estimate on a time interval Sn as 0. So you're coming back. So the wave is very focused, but you're coming back in time. So you're defocusing the wave. And you want uniform estimates up to a time which is independent of n. Okay. So two ingredients for this. The first one is modulation theory on the geometrical parameter. So here you have to use an additional parameter because since it is critical, it's degenerate, and you want another orthogonality condition or relation. So you need 3 in this case. So you need 3 parameters to modulate. And the second is to use energy virial functionals to control epsilon in a localized norm. And this was already introduced in the work of Martel Mel Raphael, and it's based on this virial estimate, but more refined virial estimate that I commented earlier. Okay, so these are the 2-MED tools, but there is something very important here. All this works because we are moving backwards. Because at some point there is a term which has a very bad sign, and this is a term in the estimate which is related to the blow-up. Okay, so you remember our scaling operator. So a term relating to this one, it has a very bad sign, but when it's very difficult to control. But then when you're coming backwards, so the wave is defocusing, this has a good sign. So you don't need to control it. And well, I think this is somewhat important. And then if you can do this, well, you can use compactness. So you know that you can extract, you have a profile and you can extract a subsequence at this time S0, which converges weakly to this profile. And then the solution is the solution which evolves from this profile. Okay, so I think I've been quicker than I thought. So thank you very much. Yeah, I just finished on this nice picture of Bergen. If some of you, I know some have already been there, but if some of you would like to visit at some point, it's a, yeah, I made some advertisement also. Okay, so thank you.